However, in this video, we're asked to factor the following polynomial, and here we have a polynomial that has degree 12, and so it could be quite difficult to factor if we don't identify it as some kind of special product of a polynomial. So one of the things to check is because it has, let's see, 1, 2, 3, 4, 5 terms, it might be a perfect power of 4. Notice that if you expand a minus b to the power of 4, we have that expands to a to the power of 4 minus 4a cubed b plus 6a squared b to the power a squared b squared minus 4a b to the power of 3 plus b to the power of 4. So one of the things to check is check the easiest terms to see if it can be written in this form somehow. So the first two terms that are the easiest to check are the first term and the last term. Now, the first term, let's see if we can write it as a to the power of, or as some power of 4. So notice that 1,296 is 6 to the power of 4. So I can write this as this is equivalent to 6 times x cubed to the power of 4. The last term is, let's see here, it is 5y to the power of, it's 5y squared to the power of 4. So since the first term and the last term are perfect powers of 4, it might mean that this is can be written as a binomial to the power of 4. Now what we need to do is we need to check all of these middle terms to see if it can be written in this form. So I've got the first term and the last term written in this form, but I need to make sure that the middle terms all match. Kind of like when I'm factoring perfect square trinomials. So the second term, let's see here, the coefficient is going to be minus 4. And then we would have, let's see here, 6x cubed to the power of 3 times 5y squared. Now, the question is, does this match our coefficient here? And if we cube 6, multiply that by 5, and multiply by negative 4, we will get this coefficient. We have x cubed to the power of 3, which is x to the power of 9, and then we have this factor of y squared. So that term matches. The next term is going to be plus, let's see here, 6 times 6x cubed to the power of 2 times 5y squared, 5y squared all squared. And if we expand this, we get 6 times 6 to the power of 2 times 5 to the power of 2, which matches the coefficient. X to the power of 3 to the power of 2 is x to the power of 6, which matches here again. Y squared is going to be y to the power of 4, so that coefficient matches. And then we have to, let's see, we've got 1, 2, 3 terms done. Now 4 terms. So now we just have to make sure that this term matches as well. So we would have minus 4, or I'm getting this coefficient from here, minus 4 times 6x cubed to the power of 1 times, bracket, 5y squared to the power of 3. So we have minus 24 times 125, which is minus 3,000. And then let's see here. X to the power of 3 to the power of 1 is just going to be x to the power of 3. And y squared to the power of 3 is y to the power of 6. So this matches, and this is a binomial that is, or a perfect chordic binomial, I guess you could call it. So we could write this as 6x to the power of 3 minus 5y squared to the power of 4. So this is pretty difficult to factor. And for sure, if you didn't recognize that this could be written as a binomial that's perfect power 4, it would be pretty daunting to factor. But you kind of have an insight based on these two terms being perfect powers of 4 to check that the whole binomial is a perfect power of 4, or that it can be factored into a binomial to the power of 4. In problem 3, we're going to relate this back to Pascal's triangle. It says, write the following in terms of a single term in Pascal's triangle. So we have, let's see here, the term in row number 3 of Pascal's triangle in the let's see, this would be the diagonal number 1. And then we have row number 3, diagonal 2. So what does that look like? If we add these two together, let's see here. Let's actually think about what Pascal's triangle looks like. Well, we would have T3, comma 1, and the term next to it is just T3, 2. So these two terms, they're in the same row, but they're in adjacent diagonals. So if I add them together, it'll give me a term that's in the next row of Pascal's triangle. So this would be T4, and it's going to be in the same diagonal as this term. So T4, 2. So this is equivalent to the term in the fourth row, or not the fourth row, a term in the row number 4, diagonal number 2. Okay. So for B, we're looking to combine the term in row number 10, diagonal number 8. When I subtract the term in row number 9, diagonal 9, let's see what happens. So let's think about, again, what this looks like. We have two terms in the same diagonal, but consecutive row numbers. So this would be T9, comma 9, and then T10, comma 9 would look like this. It would be T10, comma 9 would be down here. So if we subtract these two, we should get, if we subtract, remember that these two values have to add to this value. So if I subtract, if I do T10, comma 9 minus T9, comma 9, we would get T9, comma 8. Because these two values have to add to this value. So if I do this value minus this value, it should give me this value. So this is going to be equivalent to the term in row number 9, diagonal number 8. Okay. So sometimes if you're given a sum or a difference of terms in Pascal's triangle, you can write that in terms of another term.